So for section 4 here, we're getting into dependent events and conditional probabilities. So we're going to start with dependent events. In the last video, we looked at independent events, which are two events that no matter what happens on the first event, the second event is not affected by the first event. So for example, we looked at tossing a coin and then doing the spinner. Well, no matter what I toss on that coin, though that outcome has nothing to do with what's going to happen when I do this spinner. So those are independent events. They do not affect each other. Dependent events are events that do affect each other. And so when you look at this one here, this is kind of your key phrase. But these are events that are affected. The second one is affected by what happens on the first one. If I have these cubes in a box, so you got a blue one and two red cubes, so there are 3 total cubes. If I take one out of there and I don't put it back, well then now my probability of the second one is definitely affected by what happened on the first pick. If I pick a blue one on my first pick, well then now my probability on the second pick completely changes. There's only 2 cubes in the bag. And so this is definitely affecting my second event. So let's go through a couple examples on this one. Just laying out with the tree diagram, and really with the proper tree diagram, I would be throwing the probabilities into this. So if we said the probability that it's blue, that's 1 out of 3. This red one is 1 out of 3, and this red one is 1 out of 3. If you look at the second events, so these are the potential outcomes that you could get given that this happened. So if I pick a blue one, well then here's all that's left. It's either red or red. And so these are the 2 potential outcomes that I could get from that. If I pick this red one, here's what's left. There's either a blue one left or a red one left to choose from. And then same thing down here. So these are all this is my sample space or my possible outcomes that I could have. Typically these are just best done with multiplication. For independent events like this, this is, I'm going to suggest, the best way to go. There is a formula for this, but honestly it's like more confusing than it's worth. So it's this one here, but in most cases students don't know how to apply this to a case like this. And so my advice for dependent events is just use logic. If I was going to reach one and if I'm going to say what's the probability that I get a red and a red, well, just use logic. If I reach into this box, what's the probability that the first one is red? 2 out of 3, right? So there's 2 out of 3 that the first one is red. Now if I'm going to say that I'm going to keep that red cube, I'm not going to put it back, what's the probability that I now reach in and pull out another red cube? Well, notice that there's only 1 red cube left in the box, and there's only a total of 2 cubes left in the box. So the second event of getting a red is now 1 out of 2. And so if I multiply those together, that's where I get my probability here. So I would suggest that this is the best way to go. This is the way you would have done it back in Algebra 2 or Algebra 2 Honors. This is kind of the logical approach that we would use to that. Since this formula is just not the greatest formula for figuring out these dependent events. So let me continue on. Same thing here, and you can see for the rest of the way down, these are just kind of the logical approach to doing these problems. So I'm now drawing 2 cards from a deck. So again, keep in mind, first of all, that we're no longer looking at single events here. These are 2 separate events that are taking place. This is, if I'm not just pulling 1 card out of the deck like we did in the first 2 sections of this chapter. This is now 2 events taking place. So again, if we said probability that both are red, well, just take the logical approach. If I reach in and the probability of pulling out a red card on my first pick, well, there's 26 red cards and 52 of the cards are in the deck, so this is the probability of the first one being red. My second event is now based on this actually happening. So if I did get a red card, this is now the probability of the second one also being red. Notice there are now only 25 red ones left in the deck, and there are only 51 cards left in the deck. And so that's the setup that we would see in order to get this. Just to throw that in with the formula, just to at least give you an idea of what they're trying to tell you with this. So this is the probability of the first event happening. So like the one I was just talking about, this is the probability of getting a red card on the first event. The second event is the probability of the second event happening given that the first event happened. So this is now the probability of getting another red card given that I got a red card on the first pick. And so that's what they're trying to tell you with that formula. But like I said, the logical approach is going to be best. Another example here, and again, there's a couple places in this video I'd encourage you to just kind of pause and give one of these a try. So 30 transistors, 6 defective. We're going to randomly select 3 of those. And what's the probability that they're all defective? So it's the probability of defective, defective, defective. Well, for the first one, there are 6 out of the 30 that are defective. So 6 out of 30 that the first one I pick is defective. Given that this happened, well, now there are only 5 defective left out of the 29 remaining transistors. Given that this happened, well, now there's only 4 left on the third event out of the 28 remaining. And so that would be our setup, which we would probably just leave as a fraction in a case like this. Notice this would be the answer to 3 sig figs. So if we're ever going to 3 sig figs, this is what it would look like. Those zeros do not count as significant figures. So a really common way that people lose points on these is because of the sig figs. So a lot of people would write this as 0.005 and think that that's 3 sig figs, but these initial zeros don't count. All right. Conditional probability. So here's kind of the second part of this lesson here is conditional probability. Let me just give you a really simple example of conditional probability. If I were to ask you to guess when my birthday is, well, you would say it's the probability of that happening is 1 out of 365. But if I said, guess my birthday given that it's in the summertime, well, that changes things, right? That changes your total possible. You would say, well, instead of it being 1 out of 365, now it's 1 out of like 90 if there's 90 days in the summer. So that completely changed your sample space. The total possible that you had to choose from, you're only going to choose from days that are in the summer. So if you look at this formula that we have right here, unfortunately, the formula that's given for conditional probability in our formula packet is written in a different format. This will make a lot more sense. So my advice to you for conditional probability is to memorize this formula that you see right here. This is the one that will make the most sense to you as you move through some of these problems. So here's how we interpret this. This is the probability of something happening given that this happened. So this is your given. Notice that the given goes on bottom. So in the example that I just gave you when I said given that it's in the summertime, well, the summertime became my sample space. It became my total possible to choose from. So your given goes on bottom. This is the probability of A and B happening. So notice that the stuff that goes on top, I can only now choose from the things that are a part of this event. So when we said given that it's in the summer, right, I'm going to say, well, what's the probability of guessing my birthday on a day that is in the summer? Right, so it had to be, both those things have to be true. So let me go through with a couple examples. So you got a game of chess. Eva wins 70% of the time. In another game called Go, she wins 40% of the time. 80% of the times that Eva plays games, it's chess. So this is kind of the scenario. This one is really well done with a tree diagram. So notice that there are 2 events taking place. The first one is which game are we playing? So 80% that it was chess, 20% that it was Go. So that's the first event. My second event is whether or not she wins. So they said there was a 70% chance that she wins chess, which must mean that there's a 30% chance that she does not win. 40% on Go, so 60% that she does not win at the game of Go. So this is really important that you get a good tree diagram for some of these problems. That will really help you out. So here's the sample space. These are the possible outcomes. Notice that these all add up to 1 because that's my total sample space. So given that she won, so automatically that's here, that's my given. That's what will go on bottom are cases where she wins. So that's what we put on bottom. Find the probability that it was chess. So right off the bat, I always start with the given. So for me, that's the easiest thing to look at first. So the bottom needs to be cases where the given happened. So if we said given that she won, well, 0.56 for a win here and 0.08 for a win right here. So I'm going to add those two cases together, 0.56 plus 0.08, that's 0.08, and that's what goes on bottom. So that's the denominator, that's the given cases. Really, really important that you understand how to get the top. These are cases where both things are true. She played chess and won. Notice this can only come from the given, so it's got to be coming from a cases where she won. So we're saying, what's the probability that it was chess and she won? Well, if you look right here, here's the case where she played chess and won, so 0.56 is what goes on top. And so now if you did a little cleanup on that, this is what we could work it down to. Another case right here, given that she lost a game. So again, right off the bat, I would start with my given. Here's the cases where she did not win. That's going to go on bottom. So that's a great place to start. So if I look at the cases where she did not win, 0.24 and 0.12, that's my denominator. So those are cases, that's my given, where she lost or did not win. And now when I look at the top, remember you can only choose from the sample space. So when I have to figure out what goes on top, I can only choose from this and this, right? Because those are my total possible to choose from. So the top part of this are cases where both statements are true. She lost and played Go. So if I look for that case, here's the only case where she played Go and lost, so the 0.12 goes on top. So again, you'll always put your given on bottom, and you're always putting cases where both statements are true on top. So that's why I said on this one that she lost and played Go. And that's the case that went on top. These are some mixed review examples, so I'm not going to go through all these, but this is just some great practice, so I'd encourage you to pause in a case like this and give this one a try. These are like commonly missed questions, so really worth taking a look at. So for part A, I'll let you pause right here if you want and see if you can do that one. Same thing with part B. These are just like examples from our previous video. So I'm going to scroll down here a little bit. Pause right there. So again, on this one here, so now we're going to look at a conditional case. So we know A and B is 0.34. Here's A or B. Here's B. So for the first part of this, this is review. This is with the use of the formula from our last video on how you would find A, just with the use of a formula. So that was done here to get the 0.69. So we now know the probability of A happening. So here we go with this part. This is the probability of A given B. Always remember that your given goes on bottom. So I'm putting the probability of B on bottom. On top, this is the probability of A and B happening. So I know right here, A and B was 0.34. That's what goes on top. And that's what gets us that answer. This is why for cases like this, it is so much better that you memorize this setup and don't use the one that's in the formula packet. Use this one. It's going to make a lot more sense. All right, last example, 400 students. So they filled in this chart with the responses that are in the word problem. Preferred at C. So again, you would just total up the cases at C. So right here was 219 out of the total possible of 400. So here's a given case. Prefers vacation at C given it's a girl. Remember, your given goes on bottom. So there were 218 girls. And on top, use the and statement. Vacation and girl. So if I look for those cases, vacation at C and a girl. So right here, those are the cases where both statements are true at the same time. Vacation at C and a girl. And that's what goes on top. One more case right here. Given that they vacation at C, again, here's my given of vacationing at C of 219. So the top is the and statement. Boy and C. So if I look for that case right here, these are the 86 that were boys and vacation at C. And that's what goes on top.